Welcome back to our lecture series on structural characterization of materials. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In the previous lecture, we introduced the major microscopy techniques used for study materials, including SEM and TEM. Today, we step one level deeper and ask a more fundamental question. Why does electron microscopy work at all? To answer this, we need to understand how resolution is defined, why light microscopy reaches a fundamental limit, and how electrons, when treated as waves, allow us to see structures at the nanoscale and even at atomic scale. The key limitation in any imaging techniques is resolution. The smallest distance between 2 points that can still be distinguished as separate. In optical microscopy, this limitation was formalized by Ernst Abbe, who showed that resolution is fundamentally tied to the wavelength of the illumination. Even if we design perfect lenses with no defects, the wave nature of the light causes diffraction, which spreads out fine details. As a result, when the wavelength is large, closely spaced features blur together and can no longer be resolved. This means that resolution is not just an engineering problem, it is a physical limit. This immediately tells us something important. If we want to see smaller features, we must either use shorter wavelengths or move to fundamentally different probes. This realization is what ultimately led to the development of electron microscopy. Abbe's resolution criteria tells us that resolution depends on two fundamental factors: the wavelength of the illuminating wave and the numerical aperture of the imaging system. The numerical aperture, in turn, depends on the refractive index of the medium and the angular spread of the beam entering the lens. In optical microscopy, this means resolution can be improved by increasing the collection angle or by using high index materials such as immersion oils or spatial glass lenses. However, these improvements are inherently limited. Even with the best optical design and high index immersion media, the wavelength of the visible light remains relatively large. As a result, optical microscopes reach a practical resolution limit of about 300 nanometers. No amount of lens perfection can overcome this barrier. To see smaller features, we must move beyond visible light and adopt probes with much shorter wavelengths. In optical microscopy, light propagates through the lens materials before reaching the sample. As illustrated in the diagram on the left, when a ray of light enters a material with a different refractive index, its direction changes. This bending of the ray is refraction. By selecting lens materials with refractive indices greater than 1, we can deliberately bend and focus the beam, making beam direction controllable. As a result, refractive index becomes a tunable parameter in optical microscopy. Electron microscopy operates very differently. Electrons propagate entirely in vacuum where there is no change in medium. Because there is no refractive index contrast, refraction does not occur. The refractive index is fixed at n equal to 1 and cannot be used to control or focus the electron beam. This fundamental contrast, illustrated by the ray bending diagram, explains why refractive index plays a central role in optical microscopy but is irrelevant in electron microscopy. Electron microscopy operates under conditions that are very different from optical microscopy. Electrons travel in vacuum where the refractive index is fixed at 1. Unlike light microscopy, we cannot use immersion media or high index materials to increase numerical aperture. In addition, electron beams are highly collimated, meaning the angular spread of the beam is inherently small. Together, these constraints mean that in electron microscopy, numerical aperture cannot be increased in any meaningful way. The usual optical strategies for improving resolution simply do not apply. As a result, there is only one remaining path to higher resolution, reducing the wavelength of the electrons themselves. This is achieved by accelerating electrons to high energies. At this point, classical optics is no longer sufficient. To understand how electron wavelength depends on energy, we must turn to quantum mechanics, specifically the wave nature of matter. In 1923, Louis de Broglie proposed a revolutionary idea. Particles such as electrons do not behave purely as particles, they also exhibit wave-like behavior. According to de Broglie's hypothesis, every moving particle has an associated wavelength, and this wavelength depends on the particle's momentum. For electrons, this means that their wavelength is not fixed, it can be controlled. When electrons are accelerated through a high voltage, their momentum increases. As a result, their associated wavelength decreases. This is the key physical mechanism that allows electron microscopes to achieve high resolution. This concept of wave-particle duality is not just a theoretical curiosity. It is the fundamental reason electron microscopy is possible. By treating electrons as waves with extremely short wavelengths, we gain access to length scales far below the limits of optical microscopy. When electrons are accelerated to energies of tens of hundreds of kilovolts, their wavelength becomes extremely small, on the order of angstroms, comparable to atomic spacings in solid. For example, an electron accelerated to 100 kilovolts has a wavelength of roughly 0.04 angstroms. This is thousands of times smaller than the wavelength of visible light, which is typically several thousand angstroms. This dramatic reduction in wavelength immediately explains why electron microscopes can resolve atomic scale natures that are completely invisible to optical microscopes. At these wavelengths, atomic planes, lattice fringes, and point defects becomes accessible to direct imaging. In principle, such short wavelength would allow sub-angstrom resolution. As we will see next, the practical resolution is limited not by the wavelength alone, but by lens aberrations and instrumental constraints. There is an important distinction between theoretical resolution and practical resolution. While electron wavelengths at high accelerating voltages are extremely small, the real electron microscopes are limited by several practical factors. These include lens aberrations, mechanical vibrations, electromagnetic noise, and sample stability under the electron beam. In scanning electron microscopy, there is an additional and very important limitation, the signal generation volume. Even if the electron beam itself is extremely small, the detected signal, such as secondary or backscattered electrons, originates from a finite region inside the material. This interaction volume can ultimately limit spatial resolution. As a result, most electron microscopes achieve practical resolutions of a few angstroms rather than fractions of an angstrom. Even so, this resolution is sufficient to directly image atomic planes, defects and interfaces in crystalline materials. Electron microscopy is commonly divided into two major categories: scanning electron microscopy or SEM and transmission electron microscopy or TEM. In SEM, a finely focused electron beam is raster scanned across the surface of a bulk specimen. As the beam interacts with atoms near the surface, various signals such as secondary and backscattered electrons are emitted and collected to form an image. SEM is therefore particularly powerful for studying surface morphology, topography, and near-surface composition. In TEM, the approach is fundamentally different. Electrons are transmitted through an ultra-thin specimen, typically less than 100 nanometers thick. The transmitted and diffracted electrons are used to form images and diffraction patterns that reveal the internal structure of the material at nanometer and even atomic scales. Although SEM and TEM rely on the same underlying physics, the wave nature of electrons and their interactions with matter, they are designed to extract very different kinds of information. Together, they form complementary tools for understanding materials across multiple length scales. Before we proceed further, it is important to pause and understand how electrons interact with a specimen, because all information in electron microscopy originates from these interactions. When an electron beam strikes a solid, it does not simply bounce off the surface or pass straight through the material. Instead, the incoming electrons undergo a complex series of elastic and inelastic interactions with atoms inside the specimen. Some electrons are deflected by atomic nuclei, while others lose energy by exciting electrons, phonons, or electronic states in the material. These interactions generate a wide variety of signals. Among the most important are secondary electrons, backscattered electrons, characteristic X-rays, Auger electrons, and even light emission, known as cathodoluminescence. Each of these signals originates from a different depth and physical processes within the material, and each carries different information about surface topography, composition, crystallography, or electronic structure. Understanding where these signals come from and what they represent is central to interpreting electron microscopy images correctly. In the next few slides, we will examine these signals one by one, starting with those most commonly used in scanning electron microscopy. Secondary electrons are low-energy electrons generated extremely close to the surface of the specimen, typically within just a few nanometers. Because these electrons originate so near the surface, only those produced at or very close to the topmost layers can escape and reach the detector. As a result, secondary electrons are highly sensitive to surface geometry. This makes secondary electron imaging ideal for revealing surface topography. Features such as edges, steps, corners, and fine morphological details appear with a strong contrast, often giving SEM images their characteristic three-dimensional appearances. For this reason, secondary electron imaging is the primary mode used in SEM when the goal is to examine surface morphology and fine structural features at high spatial resolution. Backscattered electrons originate from deeper within the sample and result primarily from elastic scattering of the incident electron beam by atomic nuclei. Unlike secondary electrons, the intensity of backscattered electrons depends strongly on the atomic number of the material. Heavier elements scatter electrons more efficiently and therefore appear brighter in backscattered electron images, while lighter elements appear darker. For this reason, backscattered electron images provide what is commonly called Z contrast, making it especially useful for distinguishing different phases or compositional variations within a sample. At the same time, because backscattered electrons still originate from near surface regions, they retain some sensitivity to surface geometry. This makes BSE imaging valuable for combined compositional and topographic analysis, particularly in multi-phase materials, alloys, and composites. Some electron-matter interactions are energetic enough to eject inner shell electrons from atoms in the specimen. When this happens, the atom is left in an excited state with a core level vacancy. As electrons from higher energy levels drop down to fill this vacancy, the atom releases energy. One way this energy is released is through the emission of characteristic X-rays. These X-rays have energies that are unique to each element, forming the basis of energy dispersive X-ray spectroscopy or EDEX. Because X-rays can escape from relatively deep regions within the sample, EDEX provides bulk compositional information, typically from depth on the order of micrometer. Alternatively, the excited atom can relax through a different pathway known as Auger-electron emission, where the excess energy is transferred to another electron instead of being emitted as an X-ray. The resulting Auger electrons have very low energies and can escape only from the top few nanometers of the surface. As a result, Auger spectroscopy is extremely surface sensitive, making it complementary to EDEX. Together, these signals allow electron microscopy to probe composition across vastly different length scales, from the near surface atomic layers to the bulk of the materials. The region from which all electron-induced signals originate is known as the interaction volume. When an incident electron beam enters a solid, it undergoes multiple elastic and inelastic scattering events, spreading out beneath the surface into a characteristic teardrop-shaped volume. All signals we have discussed, secondary electron, backscattered electron, X-rays, and Auger electron, originate from different regions within the volume. The size of the interaction volume depends strongly on the accelerating voltage and the atomic number of the material. Higher accelerating voltages give electrons more energy, allowing them to penetrate deeper and generate a larger interaction volume. Similarly, lighter elements scatter electrons less effectively, also leading to deeper penetration. In contrast, lower voltages and higher Z materials confine interactions closer to the surface, which is particularly useful when surface sensitivity is desired. By carefully adjusting beam energy, detector geometry, and even sample tilt, we can selectively enhance certain signals over others. This control allows electron microscopy to be tailored for topographic imaging, compositional contrast, or surface-sensitive analysis, making the interaction volume a central concept in interpreting SEM and TEM data. To summarize, electron microscopy achieves its extraordinary power by combining extremely short electron wavelengths with rich electron-matter interactions. The electron wavelength fundamentally determines the achievable spatial resolution, allowing us to probe structures down to the atomic scale. At the same time, the various interaction mechanisms between electrons and matter determine what types of information we obtain, whether it is surface topography, composition, or crystallographic structure. In the next lectures, we will build directly on this foundation as we explore analytical electron microscopy, including techniques such as EDEX, EBSD, and more advanced spectroscopic methods. A clear understanding of the physics behind these signals is essential, not only for using electron microscopes effectively, but also for avoiding misinterpretation of images and data. As we move forward, keep in mind that every image in electron microscopy is a consequence of both wavelength and interaction physics.